recording. Okay. And then I hope you found, let me go ahead and let's see, share screen. Okay. So now we are recording and I'm sharing the screen. So if you want to go back and see the video that we posted from our first discussion, it'll be in media gallery. So we'll just give it a second to load. Here we go. So the professor's lectures, and then this one is discussion 1, TA Maria. And that's where I walk you through everything. Okay, let's see. A student is asking just to 100% make sure the discussion quizzes are based off of the previous week worksheet. So it could be the previous week worksheet and any concepts we've gone over. So it doesn't necessarily have to be the worksheet. It could be this week's worksheet too, since you do have until the following Monday to do it. So it should just be like any worksheet that you've seen up to that date of the quiz, of when the quiz is due. Okay, and then today I'm gonna actually start off with a little bit of review to help you prepare for that quiz. I just want to make sure you guys know how to find the videos. And then I also if you don't know where to find the videos, if you go to announcements, I went ahead and linked the first 2 videos because students might forget like where the videos are. So links to videos with example problems and answers. So I just linked the first 2 videos, but if you go to any of those, you should be able to find the rest of the videos. Okay. Okay, so I hope all of that was useful for you. And then now we can go ahead and get started. Let's see what the chat says. Okay, you're welcome. So let's see here. Discussion problem number 2. Okay, so these are a discussion worksheet, 1, 2, 3 problems, but it actually ended up being a lot of work. It's pretty long. But before we get there, I want to start off with a little bit of review from last week for your quiz. Okay, so definitely maybe take notes or you can make flashcards at a later time. Okay, so we're going to be talking about, like, sometimes you'll have problems that'll say like, oh, which of these molecules is more soluble in water? So we're going to discuss that right now. So I'm going to give you an example. So you can have a multiple choice question and you can have like a molecule right here and you can have another molecule right here. Let's see, can I write with my hand? Yeah, okay. And then you can have another molecule like this. And then this will have like hydroxyl groups. So if you guys remember the concept of electronegativity, you will remember that the bond between oxygen and hydrogen, so this hydroxyl group, is polar because the electronegativity value of oxygen was like 3.44 and the electronegativity for hydrogen was like 2.2. So when you subtracted those, the electronegativity difference was like 1.2 something or something. So the point is that that electronegativity difference was more than 0.5. And if the electronegativity difference is more than 0.5, that means that that bond is polar. And when something is polar, it is hydrophilic. It is water-loving, and it will dissolve in water. It loves being in water, okay? So that's what you have here. And then when you have, so I hope you can recognize that this is all CH3s. So like this right here is a carbon. So you can have like 3 little hydrogens attached to that carbon, right? And because every carbon has 4 bonds, so this would be one bond. I'll make this big. This would be one bond. This would be another bond. 2, 2, 3, 4. And then in right here, you have your carbon. So here is another carbon. And so it already has 1, 2 bonds. So you can just add like another 2 hydrogens. So this is a hydrocarbon chain. And at the end, it has a CH3. So what we learned last week about the electronegativity values between carbon and hydrogen is that their electronegativity values are really similar to each other. So their difference is less than 0.5. So this is not polar, non-polar. So if it is non-polar, then it is hydrophobic. And that means that it does not like to dissolve in water. Okay. So when you get a question like this and you're like, oh, which one of these is going to dissolve in water? Can you guys guess? You can either put it in the chat or speak up. No? Okay. If you're shy, it's okay. So basically this molecule right here would dissolve in water the most. And then these guys will not dissolve in water. Okay, so out of all these 3 molecules, which one would be the least hydrophilic? Yeah, the one with the oxygens. Yes, good job. Okay, yeah, the question was which of these molecules will dissolve in water, like will love to dissolve in water. And yeah, it was the one with the hydroxyls because that's a polar bond and they love to dissolve in water because water is also polar. And so these guys right here from these 2, which one will hate to dissolve in water the most? So I'm just going to give you the answer. Oh, some of you, let's see, the one that wouldn't would be the longer chain. Good job. Yeah. So yeah, the longer chain, because it's longer, it has more carbons and hydrogens, it would be the least likely to dissolve in water. It would hate it the most. And then the shorter chain one would hate it also, but not as much as the longer chain one. So good. If you guys were able to answer those questions, that means that you do understand the concept of electronegativity, which is great. So let's see, what else did I want to, okay. So for your first problem here, suppose, I'm going to read the problem first, and then I'll go ahead and walk you through it. So suppose the major solutes in intact lysosomes are potassium chloride. So we're talking about a lysosome, that's just an organelle inside of the cell. And for me to be able to understand a problem, I love to draw it out. So we have a lysosome. Actually, I'll draw it out over here, I think. Let's see. Yeah, I made some notes down here, so I'll just draw it out right here. So this is a lysosome right here. So now it's saying, okay, you have a lysosome, and the major solutes in an intact lysosome are potassium chloride and sodium chloride, and then they give you the concentrations. So inside of this lysosome, you have sodium chloride and potassium chloride. So when isolating lysosomes, what concentration of sucrose? So sucrose is, I don't know if you guys remember, but potassium chloride, these guys dissociate into potassium and chloride. So this one molecule will dissociate into 2 ions. And so when we're talking about osmotic pressure, that means that the I will equal to 2 because I is how many molecules you have. So this is why it's important to know your formulas. So I'm just going to go ahead and remind you guys right here. So I equals 2 for potassium chloride because it will dissociate into 2 And then for sodium chloride, the same thing happens. It also dissociates into 2. So I equals 2. Okay. So in the formula, we're using I equals 2. And then, so when isolating lysosomes, what concentration of sucrose is required in the extracting solution? So now they're saying sucrose, and sucrose does not ionize or dissociate into 2. It remains 1 molecule. So we're just going to put I equals 1. So whenever it's time to include sucrose in the formula, it's going to be really easy. We're just going to say I equals 1. Okay. Okay, so they're talking about extracting solution. So this is the lysosome. The lysosome has, let's see, potassium chloride, so potassium chloride, and it also has sodium chloride. And then in the extracting solution, you have sucrose. Okay, so calculate how much sucrose would you need. Oh, okay, hold on. So the extraction solution at room temperature. So the room temperature has to be a part of the equation. And we say 25 degrees Celsius, but we already know that in all of these equations, we need everything to be in Kelvin. And it says to prevent swelling and lysis. So what are they talking about here? Because there's a lot going on in this problem. It is not easy. So we're breaking it down to make it easy for you guys. So first of all, swelling and lysis, they want to prevent it. So you have to remember some important terminology that was in video 1. So if you haven't watched the video, I'm just going to go over it really quickly. So if you have, let's see here. Okay, so if you have a lysosome, let me delete that, or we'll just leave it. Okay, if you have a lysosome, no, let me delete that. Delete. Okay, let me draw bigger. Okay, so you have a lysosome or anything, a cell. And if you have a lot of hydrogens in that cell, or whatever it is you have in the cell, anything you have in the cell, if you have a lot, let's say you have like 1,000 inside, but outside there's only 1. So when you talk about osmotic pressure, you're talking about like the solution. So we're talking about tonicity. So here they're talking about the solution. So it's whatever's outside. So like whatever is out here. So that is less than what is inside. So this would be considered a hypotonic solution. Hypotonic solution. Okay. So anytime they ask you if something is hypotonic, hypertonic, isotonic, they're asking you about the solution. Okay. So now I have this right here, and I'm going to have 3 inside and 3 outside. So what do I have here? Well, they're the same. So I'm going to write a little bit smaller. So this is isotonic. This is an isotonic solution. Okay. So now I'm going to have a cell or whatever here, and then I'm going to have only 1 little hydrogen on the inside, and I'm going to have a lot on the outside. So in terms of tonicity, this solution is on the outside. The solution will be hypertonic. So this would be a hypertonic. So if you don't know this by memory, then definitely make some flashcards, and you have to know it by heart so that you're able to answer these complex questions a lot faster. Okay, so now another important thing is that water follows the salt. That's what I always like to say, water follows the salt. So in the first scenario, it's going to be like that, or water follows the ions. So in this scenario of when you have a hypotonic solution, water is going to go into the cell and the cell is going to expand or swell. And that's what they talk about in those. So this is something you also have to know for your quiz, this concept. And it always shows up on exams too. So definitely know by hand. So here, or know it by heart. So here, I'm just gonna make extra notes for you guys. Okay. Okay, so water, let me move. Water goes into cell and cell expands. And the word that is being used is swells. I'm just gonna put that in parentheses, swells. Water swells, okay. Or the cell swells, okay. So, okay, so then right here we have the isotonic solution. So here, water doesn't follow anything because everything is perfectly balanced. Everything is balanced. So we're just gonna say water doesn't, I'm just gonna say balanced. So because it's balanced, cell remains the same size, okay? And then over here on the last scenario, so water is going to follow these guys. So when you have a hypertonic solution, water will leave the cell and cell shrivels. I'm trying to remember if the professor used a different word other than shrivels. The cell will dry up, basically. Just gonna leave it like that. Okay. So I hope those concepts are really easy for you guys to understand now, because now we can understand our problem. It's saying, suppose the major solutes in an intact lysosome are potassium chloride and sodium chloride. When isolating lysosomes, what concentration of sucrose is required in the extracting solution at room temperature to prevent swelling and lysis? So they do not want swelling and lysis. So which of these three conditions are they talking about? Yeah, so if they don't want swelling and lysis, they're talking about the balanced condition. They want the cell to remain the same size. And that means that they're telling us that they want an isotonic solution. So however much salt or solutes are inside the cell, we have to make the exact same amount outside the cell in the extracting buffer. So that is why it was super important for you guys to understand this concept, because if not, you would get this whole question wrong. Okay, so that's why I focus so much on the concepts. Okay, so now that we know that, it's asking us calculate how much sucrose, and then they give us the weight, like 342.3 grams per mole. That's how much sucrose weighs. Would you need to make, and then this is the volume that they want us to make. And so with moles, with a mole, it's like per liter. So here 500 mils is equal to 0.5 liters. Okay. All right, so now we can go ahead and get started on the math and stuff. So I also have this example in my video. I think the numbers might be different, but I walk you through the entire process in case you need like an additional example to make sure you feel comfortable with this. But let's go ahead and follow my notes for now. Okay. Okay, so because potassium chloride will dissociate into two molecules, we know that, actually, let's go ahead and start off with our formula. Let me put it right here for you. Okay, so we have our osmotic pressure is equal to RT, which was the universal gas constant, and temperature in Kelvin, times I, which was the number of like molecules that you have, so or ions. So sucrose, if you remember, I equals 1 because sucrose does not dissociate into 2 or 3 products. It just remains one product. And then times the concentration. Okay. So that's our formula that we're working with. And C is the concentration in molarity. So they did give us the concentration for potassium chloride and for sodium chloride. Okay, so that's what we have here. And then let's see. Okay, so the first thing that we have to remember is that let's go ahead and undo that. Okay, so the osmolarity of we just determined that the osmolarity of the lysosome has to equal the osmolarity of the extracting buffer. So that's going to make these calculations easier, okay? Because the osmolarity has to be the same. Okay, because we want this to be an isotonic environment. Okay, so now I'm going to go ahead and start walking you through the math. Here we go. So the osmolarity is equal to RT times the concentration. So we're going to do potassium chloride first because that was the first one that they gave us. And potassium chloride was 0.1 moles and the I equals 2. So we just do I, which is equal to 2. Oh, yeah. I was supposed to have the little parentheses. Okay. Okay, so we'll make this a little bit bigger, parentheses. So the I is 2 times the concentration, which was 0.1 molarity, and that's for potassium chloride. And then we just, because we have 2, we would be done if we only had potassium chloride inside the lysosome, but they gave us 2 little guys, okay? So you don't have to be scared. It's better that they did it this way because if they give you 2 on an exam, you should know how to do it. All you do is you put a little plus, and then you go ahead and work out the I for sodium chloride, and that's I is equal to 2 as well, because it dissociates into 2 ions, and then we add our molarity, our concentration, and that is 0.03 moles, molarity. Okay, and so when you do the math, you get osmolarity equals RT and 0.26 moles per liter. So that's what molarity is. This giant M, it's just moles per liter. So you can write it as the capital M, or you can write moles per liter. It's fine. So this is the osmolarity we need for the extracting solution. So remember, you can either go ahead and add in the RT, but you don't really have to because they cancel out, because the osmolarity of the lysosome is equal to the osmolarity of the extracting buffer. So the whole RT, it's going to be on both sides and they can just cancel out. You don't really need to put them in there. That's why we just do this much math and then that's it. So this is the osmolarity for the lysosome. And because this is going to be an isotonic solution, the osmolarity for sucrose has to be exactly the same. So it's part of the answer, 0.26 moles per liter for sucrose. And then we have to take it one step farther. Actually, a few steps farther. So now we're going to go ahead and use all the information they gave us. So the concentration of sucrose is 0.26 moles per liter. Now, they told us how many liters, right? They said 500 mils. And so that was 0.5 liters. So all you do is set it up like this. And you say, okay, well, 0.26 moles per liter times 0.5 liters. And then the liters cancel out, and that equals 0.13 moles. Okay. And then they gave us a little bit more information. They said for sucrose, it is 342 grams per mole. So you just do 342 grams per mole. And then again, that cancels out. Okay. And then that equals 44.46 grams. So that's the answer. We had to do a lot of math. It was, so I would practice this problem on several sheets of paper a few times, you know, just go through it a few times until you understand exactly what to do and when, without having to really look at your notes for the next step. But basically, this is saying that if you want the same concentration or the same osmolarity in the extracting buffer, which is sucrose, as you have inside of the lysosome, so that the lysosome does not expand and does not shrivel up, you need 44.46 grams of sucrose, and you need to dissolve that in 0.5 liters, okay? And that's how you do that entire problem. Does anyone have any questions right now? Okay. Looks like we're good. So we'll go ahead and move on to the next problem. Understanding and working with pH and pKa is very important for this course. Oh my gosh. Okay. Everything to do with pH and pKa, please make flashcards. There are certain definitions and then there's certain rules that you just have to know. And you absolutely have to know them in order to be able to answer these problems. Okay. So here we go. And we probably won't get through the entire worksheet. We definitely won't. So I just wanted to show you guys. This is video 1 towards the end, and this was the example that I was telling you about. And then after that example is a beautiful example about pH. And then I think I go into like several problems about the pH and pKa and all that. And you have to know how to do that for your exams and quizzes. So definitely check this out. Take your time with it. And then I went ahead and gathered all of the formulas for you here having to do with pH. So pH plus the pOH is equal to 14. So just as a brief overview, pH is how many hydrogen ions or how many protons you have in a solution. Okay, so that's a pH. Now pOH is how many hydroxide ions you have in solution, because if you remember, water molecules, they ionize, and you start off with H2O, and that turns into, you know, hydrogen ions and hydroxyl ions. So that's all that this is talking about. So whatever your pH, you add that to your pOH and it will always equal 14. So if your pH is 4, then your pOH is 10, because together they have to equal 14. So if your pH is 1, then your pOH has to equal 13, right? Because they have to equal 14. So that's super easy, right? Okay. Now we have pOH is equal to the negative log of the hydroxyl concentration, or hydroxide ion concentration. So they will give you a value. When they do, you put it in here and you just use this formula. And that will give you the pOH. So if they give us a value and our POH was 10, you have to be very careful because on exams they'll give you all the information to determine the POH, but then the final question is what is the pH? And I've seen so many students lose the whole question just because of that. So you have to be very careful with what they're giving you, use the right formula, and then what is the final thing that they are asking for. So if you found out that your POH here was 10, go back and reread the question. If it says, what is your pH? Then that would be 14 minus 10, and it would be 4. Your final answer would be 4. Okay, so it's like super simple math, but you have to make sure you're on top of everything. Okay, so now the next formula is pH is equal to the negative log of the hydrogen ion concentration. So that's exactly the same as a POH, but now it's a pH. So you do the exact same thing. And then we have pH is equal to 14 minus POH. That's the same formula as the one on top over here. And then our last formula for pH and pKa, pH is equal to the pKa plus the log of A minus divided by HA. So this would be our acid, okay? So now we're talking about acids. So HA is the acid. Remember, acids have more protons. And then A minus, this is when the acid has already donated its proton. So now it has a minus side. We call this guy the conjugate base. So this is all the terminology that I'm talking about. You really have to know your terminology. So again, the acid, that's HA, because it has the proton still. But whenever the acid donates its proton, you end up with A with a negative charge. And so that is the conjugate base, okay? So if you know these formulas, then you're gonna be able to answer any question they give you, okay? And so that's what we're gonna do right now. We're gonna go ahead and start the next question. I think there was like a picture I wanted to show you guys. Let me see. Yeah, okay. Okay, so since we're going to be covering acids a lot, I wanted to show you guys this right here. So if you have something with a lot of hydrogens, I'm just going to draw the pluses because hydrogens, we also call them protons. We use the terms interchangeably. So on an exam, I don't want you to be confused if someone tells you hydrogens or they tell you protons, just know that they're basically the same thing. Okay, so we have a lot of hydrogens in the top one and a little bit in the bottom one. So here is where I'm going to give you some terminology so that you really understand everything moving forward. Okay, so this has a lot of hydrogens. So this would be acidic, okay? Because acids, they have a lot of extra protons. So this is acidic, and the pH is less than 7. So if I tell you, oh, the pH of the cell is 3, is it acidic or basic? Well, if the pH is less than 7, it is acidic. If I tell you the pH is 6, is it acidic or basic? Well, it's acidic because it's less than 7. And so there will be like super complicated problems down the road, but sometimes they just give you a picture like this or they describe it, and it is up to you to fill in the terminology so that you can eventually get to the right answer. So many of my students have lost or gotten 0 points on 10-point problems on exams because they confused this concept. Okay, so that's why I'm really spending the time right now to make sure you guys understand it. Okay, so if there's a little bit of hydrogen ions or protons, then this would be considered basic. And anything that is basic is when the pH is greater than 7. So if I tell you, oh, the pH here is 13, is it acidic or basic? Well, you're going to tell me, oh, it's basic. And then if I tell you, oh, there's a lot of protons in there, is that acidic or basic? You're going to say, oh, that's more acidic. If I tell you, oh, there's a little bit of protons in there, and that's all I tell you, then you should know automatically that that is a basic solution and that the pH is more than 7. Okay, so there's things that you have to be able to just know. Okay, because they're going to give you clues like that when in unwritten problems. Okay, understanding and working with pH and pKa is very important for this course. 1. Water is a weak acid. Write the ionization reaction of water and the equation that describes its Ka. So Ka is acid dissociation constant. And so that just means when water wants to give away its proton. So they also use the terminology lose. When an acid loses its proton, I like to say give away. So for the rest of the semester, I'm just going to be saying, oh, when that acid decided to be nice and it's in the right mood, and so it is willing to donate its proton. Okay, so here the equation, and so they're gonna give you other weak acids, and you're gonna have to write the dissociation equations also. So pay attention here. It's really easy. So here we have H2O, okay, and that just turns into this. A proton or a hydrogen ion plus a hydroxyl or a hydroxide ion. Easy, right? And that's it. Okay, so one thing that we have to constantly remember is that this is a reaction because we have the forward and the backward arrow. So whenever you have a reaction, you want to make sure that you label your reactants, okay? And then let me put that guy, yeah, right there, it's fine. Okay, you have your reactants, and then these guys over here are our products. So knowing which ones are your reactants and which ones are your products, that's really important for all the equations that are gonna come next. Because for all of your equations, it's always products over reactants. So you need to know who your products are and who your reactants are. Okay, yeah. So for example, they give you guys this one right here. So let's see. So Ka, so the acid dissociation constant is equal to the products, which was the hydrogen ion or the proton, times the concentration of the hydroxyl ion, divided by the reactant, and the reactant was just water. Okay. Okay, and then that's it for that. So B, what is the concentration of hydrogen ion in a solution of water when the concentration of hydroxyl or hydroxide ion is 10 to the negative 8 moles? What is the pH of this solution? What is the pOH? So they're asking you a lot of things here. Okay, so what is the pH? What is the pOH? And is the solution acidic or basic? So based on everything we just learned, this should be pretty easy, but I'm going to walk you through it anyway. So what is the concentration of hydrogen in a solution if the water when the concentration is OH? So now we have to use one of those formulas that I showed you. They're giving us the OH concentration. So the solution that we're going to go ahead and use is this one. pOH is equal to the negative log of the concentration of OH. Okay, minus. Okay, so that's super easy, right? So then all you do is just fill it in. POH is equal to the negative log of the concentration of OH minus. And they told us that the concentration of OH minus is 10 to the minus 8 molarity. So we go ahead and do that, and our answer is going to be 8. So we know that our POH is equal to 8. And so that answers one of our questions. They said, what is the POH? But they're also saying, okay, so this is POH. But they're also saying, what is the pH? Okay, so the pH is just 14, take away 8, right? Because the pH plus the POH is always 14. So when you have one, you just subtract it from the other one. So 14 minus 8 is equal to 6. So our pH is equal to 6. And then it's asking us, is this acidic or basic? Well, so remember, students lose points here because they'll look at the POH and determine acidity. And we can't do that. We cannot do that. We can only look at the pH to determine whether something is acidic or basic, okay? We can only look at the pH to determine whether something is acidic or basic. So the rule was that if it was less than 7, then it was acidic. And if it was more than 7, then it was basic. So here we know that this is acidic. And yes, some of you answered correctly, which makes me happy because that means you're understanding the material and you're able to follow along. So that's fantastic. Okay. So what is the difference between pH and pKa? How are they related? Draw a titration curve for a molecule with pKa is equal to 4.7 and label all the axes. Okay, so this always shows up not just on one exam, but multiple exams, the final. You really have to understand this material. I don't have time to walk you through it because we only have 5 minutes. Like I can try, I'll do some of it, but I did spend a lot of time walking you through it, I believe in video number 2. And I think I did a really good job of explaining it. So yes, here it is. Yes, awesome. Okay. Yeah, like definitely watch video number 2. I give you definitions about acids and bases, all the formulas again, and then some. Yeah, I really walk you through everything here. So please watch that. But in the meantime, I'll try to go through this as like as much as I can. Okay, so what is the difference between pH? Draw a titration curve for a molecule with a pKa of 4.7. So remember, the pKa is just the pH at which that acid wants to lose its proton. So some acids are really friendly, and we call those really strong acids. And those will lose their proton at a really low pH. But other acids, they're more stubborn and they're not so friendly. So you have to get a really high pH in order for them to donate their proton. Okay? So here they're asking you for a titration curve where the pKa is equal to 4.76. So you're going to start like this. This is going to be our titration curve. Okay, over here we're going to have our pH, and down here is going to be our POH. And here we're talking about one proton. You can have a titration curve where you're giving off multiple protons, like 2 or 3. And so right here, I'm just going to show you what one proton looks like. Okay. And so if you had because you have to know the other ones too. If you were giving off 2 protons, like some acids have 2 hydrogens to give, they will look like this. Okay. And then if you have 3, it'll look like this. Okay. All right. So right here in the middle, this is where, from our titration curve, this is where the pH is equal to the pKa. So pH equals pKa. So they told us that the pKa is 4.76. So the pH here is 4.76 and the pKa is also 4.76. Okay? So now, so for pH, we're going to go ahead and write, you can write those numbers down. So you just want to like double it. So 4.76 and 4.76 is like about 9. And then right here, we can say this is 4.76. Okay. That's how we know where we are. And then we're going to talk about like, this is going to be 3 right here. And we're going to talk about a carboxyl group. So carboxyl groups, let's see. Okay. So a carboxyl group is a COOH. Okay. So COOH. Okay. And that has a pKa value of about 3. So it will lose its proton or donate its proton at a pH of about 3. So down here, the pH is like 2. So here it has not donated its proton. But up here, when we're up here, we are at a pH of about 9. So we are at a really high pH. So at this point, this carboxyl group, it already donated its proton. So you will find it as COO minus. Okay. And anytime after its pKa value, which was about 3, if we're like at a pKa of about 5, then it's already starting to lose its proton. Okay. But by the time you get to like 9, then it's already lost its proton completely. And another thing that's really important that'll show up on exams, they'll ask you about buffering region. So what will be the buffering region for this thing right here? So because they told us that the pKa is 4.76, it's really easy to determine the buffering region. All you do is take 4.76, take away 1. So that would be 3.76. And then you do 4.76 plus 1, and that'll be 5.76. So the buffering region for this would be from 3.76 to 5.76. Okay, so go ahead and try to work the rest of the worksheet by yourselves using my videos as help. And then if you get stuck, please come to my office hours. I think I'm going to have them on Friday again. Just look at the Zoom on CAT courses. And yeah, just come to office hours and I can help guide you through. If you have any questions, go ahead and let me know. If not, have a good night.
Cool.